Hi everyone. I think since it's the placement season, I'm receiving a lot of questions related to analog circuits. So I thought I'll reply to a few YouTube comments. So I was just scrolling through the comments and I found two of them were more conceptual in nature, and remaining questions were numerical. I think I'll leave it to you. You can discuss it among yourselves. So these two questions are related to, one is related to a resonant LC tank or a parallel or series LC tank. The other one is related to a Schmitt trigger. Okay. So the first question is this. We have discussed for an LTI system that we know for an LTI system, if you feed a sinusoid of frequency omega I, then the output should contain the same frequency. The output frequencies in of this LTI system cannot contain any frequency other than omega I. So that's what we have discussed. Okay. So this comes from the basic definition of LTI systems. But for this circuit, it turns out, I didn't get time to go through the entire video, but I'm assuming it's some parallel or series LC tank circuit. It's a resonant circuit. I have discussed in the video that there are two different frequencies. There is the input frequency and there is also another frequency, omega naught. How can a system have two different frequencies when it is linear, right? So it's a linear system, means this system, it's an LC circuit, so it is built using linear circuit elements. Inductors and capacitors are linear circuit elements. Okay, so how can you have a different frequency when you have a linear system? Okay, that's the question. So the question is something like this. You have a series LC tank or a parallel LC tank. I'm feeding a current source to the parallel LC tank, and the current source happens to be a sinusoid, say cos omega IT, and this is what some I naught times this. I'm feeding it to this LC tank, right? It's an LC tank with a certain frequency response, and we know how to find the voltage response from the if you know the input and the frequency response, then you know the final output response. Okay, so from that linear analysis, we can see that output cannot have any other frequency. Output should also have the same frequency as omega I. Okay, omega out should also be equal to omega I. Why is there a different frequency? We'll try to understand that. To do that, first I'll just go back and revise the basics of LTI systems. So if I have an LTI system with an input x of t and an impulse response h of t, okay, this is an LTI, linear and time invariant system. The output y of t for this LTI system will have two components. Okay, whenever you want to find its output, you're feeding an input, the output can have two components to it. One part of this output is what we call forced response. This is the response that's present because of the input. If I make my input go to 0, x of t is 0, then there is no forced response. So this response will go to 0. Okay, so this forced response is the response of the system because of the input. Then there is another response which is called natural response. Okay, so this comes from a fundamental theory of differential equations also. You don't even have to go to LTI systems. Any linear differential equation, solution to any linear differential equation can be written as this form. It can be written as sum of two components, where one component will depend upon the input to the differential equation. X of t is the input to the differential equation, or input to the differential equation, and y of t is the output. So it will have two components. One depends on the input, which is what we call forced response. The other one depends upon characteristics of the system. Generally it depends on poles and zeros. So this is what we call natural response. So the natural forced response is what we discuss normally. When we talk about LTI systems, we usually talk about forced responses, because that's what, when you're designing amplifiers, when you measure frequency response, all you're trying to do is to guess or predict this forced response. Okay, so the forced response is simply convolution of your input signal with the impulse response of the system. Okay, and this forced response, how do you find out? If you know the frequency response of the system, h of f, which is the Fourier transform of h of t, then multiply your input Fourier transform, you get the output signals Fourier transform. Okay, so now if you see, x of f is the input here, h of f is the system. So if I apply any sinusoid here, the output will also contain the same sinusoid, and the magnitude and the phase of that sinusoid is determined by magnitude and phase of the frequency response term h of f. Okay, so that's a well-known thing, so I won't go there. So this is something we know very well, and so this is what, when we teach frequency response analysis, this is what we focus on. Okay, so when we say an LTA system, we say this is what the output is. What we usually don't talk about is the natural response also. Ideally, for a stable system, if your system is stable, this natural response in the steady state will decay down to zero. It will go to zero. Okay, so when I say stable system, all your poles of the system, h of f, h of s, you find the transfer function, all its poles should be in the left of s plane. If all the poles are in the left of s plane, then the natural response will either decay down exponentially or it will be a decaying sinusoid. Okay, so eventually it will go to zero. So in the steady state, when you measure the output is purely due to the forced response. Okay, the natural response would have completely decayed down to zero. So now I think you can already guess why the circuit is producing two different frequencies. The system in question now is not a stable system. Now this system has two poles on the j omega axis. So I just said, if you have a stable system, for a stable system, in the steady state, your output is just dependent upon the forced response, because what will happen to your natural response, that will vanish to zero. Your forced response will completely determine your output in the steady state. This is true for a stable system. The moment you have poles on the j omega axis, these systems are what control engineers call them as marginally stable systems. Okay, and for circuit engineers, this is unstable. I mean, if you have poles on the j omega axis, we call it as unstable systems because they are oscillators. Okay, and why do control engineers call them marginally stable systems? Because the definition of stability from a control theory point of view, if you feed an input signal of finite amplitude, if you feed a bounded input, the output should also be bounded, okay, with some amplitude A out. Okay, so if the output is finite, then we say that the system is stable. So this is what we call bounded input, bounded output stability. So based on this criterion, that system is stable, but we call it marginally stable. Why do we call it marginally stable? Because when you have a system with poles on the j omega axis, if you apply sinusoids of any frequency other than omega naught, if you apply sinusoids of frequency other than omega naught, the output will be finite. You will get some finite output. But if you apply a sinusoid of same frequency as omega naught, or of the resonant frequency of system, then the output will grow linearly to infinity. Okay, the amplitude of the sinusoid will grow linearly to infinity. I have discussed intuitions behind why will it grow to infinity in one of the videos. You can watch that, but let's not go there. Here the question now is, we'll come back to this system. Now this system is a marginally stable system because it has poles on the j omega axis. Whether it's a parallel LC tank or a series LC circuit, okay, both these circuits will have poles on the j omega axis, and those poles can be easily shown to be omega naught will be equal to 1 by root LC, and the poles of the system SP will be equal to plus minus j omega naught. Okay, so you can derive the transfer function and show it yourself. For a marginally stable system, the natural response is a sinusoid. Okay, so for a stable system, the natural response would have decayed down to zero in the steady state. As t tends to infinity, natural response will tend to zero. But because this is a marginally stable system, your natural response will always keep on oscillating between two values. It will be a sinusoid. So now you will have two responses, the forced response plus the natural response. The forced response will contain a frequency which will be the same as input frequency. The natural response here has a frequency which is the resonant frequency of the system, which is why now you see two responses. Okay, this is true for a marginally stable system. So for a marginally stable system, you will produce, your output will have two different frequencies. One is the input itself, and the other frequency will be your resonant omega naught or omega n, whatever I called it, will be the resonant frequency. Okay, so that omega naught comes from the natural response of the system. Okay, so this is true for a marginally stable system. Unstable system, if you have complex poles on the right of plane, then yes, it will also have some frequency, but its amplitude will keep growing to unbounded. It will eventually blow up to infinity. Okay, so now I have to reformulate my statement. I mentioned sometime in one of my old videos that for an LTI system, if your input frequency is omega I, output frequency should also be omega I. Your output cannot contain any frequencies that are not present in the input. Now I'll probably amend some words to that. Instead of saying an LTI system, I'd probably say a causal and a stable LTI system. Okay, in fact, probably I should say a stable LTI system. For a stable LTI system, if I apply a sinusoid of frequency omega I, then this condition holds true. Your output frequency will also contain only the input frequency. Okay, frequencies or energy at the input frequency. What we have in the circuit, the question that the student posed, was actually a resonant system. It's a second order resonant system with poles on the j omega axis, and therefore it is no longer a stable system. It is a marginally stable system. As far as circuit engineer is concerned, we can still call it as an unstable system. Okay, because of which it has two frequencies, omega I and omega naught. So this will be true for marginally stable systems. For unstable systems, what happens is that your output frequencies may not even be related to, when I say unstable, I mean systems that don't obey the BIBO stability, bounded input, bounded output stability criterion. Those systems, you cannot even say what kind of frequencies will be present at the output. Your system will be simply saturated. Okay, your output will simply be saturated. So once your amplifier is saturated, it's not even going to amplify your signal anymore. So you can't even give any frequency relations between input and output. So that's my answer to that. So I hope that cleared it out. So for a marginally, because it's not a stable